In this video, I'll be showing that given two subspaces W1 and W2, so we have two subspaces of V, which is a vector space. So given two subspaces of a vector space V, we want to show that the sum of these two sets, or these two subspaces, is also a subspace of V. Now, notice before we start this problem, if any of you have taken or are taking linear algebra, this isn't not a direct sum. Direct sum. So if you haven't taken linear algebra and this is the first time you do, then just ignore this. But for people who might have and are wondering, well, is it the sum of two sets or is it a direct sum? It's not a direct sum, it's just the sum of two sets. Now, I'm going to give you a quick definition of what it is to actually sum two sets together. So definition of the sum of two sets, right? So we define the sum of two sets. So let's take W1 plus W2, since it's conveniently the problem we're trying to solve. So this is actually a set in itself, but how do we define it? Well, we say that the set W1 plus W2 contains the elements. So a set is something that contains elements or objects or vectors, whatever. So it's a set that contains the elements x plus y, where, and this is important, so this is such that x belongs to W1 and y belongs to W2. Okay, so basically what this is saying is that any element in W1, W2 is expressed by the sum of an element in W1 and an element in W2. So in other words, what that means is if you have, let's create an arbitrary element that belongs to W1 plus W2. So if A belongs to W1 plus W2, okay, then this means, according to this definition, that A can be written as B plus C. So I'm just creating two elements, okay, and the first element B belongs to W1, and the second element C belongs to W2. So for any element that belongs to W1 plus W2, it can be expressed as the sum of an element in W1 plus an element in W2. So that's the definition of the sum of two sets. So I need to define what I'm trying to find first before I get into proving that it's a subspace. So that was a more or less quick definition. So now, if you haven't seen the other video about how to prove a subspace, I'm going to give you a quick recall on how to show that something is a subspace. So in this case, I want to show that W1 plus W2 is a subspace of V. Okay, this is the shorthand notation in linear for subspace. So this is subspace. Okay, so there's three conditions that I need to check. Three conditions. The first one is I want to see if the zero vector belongs to W1 plus W2. The second condition is I want to check that if x and y are two arbitrary and distinct is very important, so x and y can't be the same. X and y are two distinct arbitrary elements of W1 plus W2, then if we add these two elements together, if we add these two, x plus y will belong to W1 plus W2 as well. So given this, we want to show this. And then finally, the third condition we need to check for something to be a subspace is given an arbitrary element of W1 plus W2, x, so I'll just call it x, and a scalar c belonging to the real numbers, then I want to see if I rescale x by c, I want to see if cx, right, so the scalar multiplication of x by c, if this operation also belongs to W1 plus W2. So these are the three things I need to check to see if something is a subspace. Check for subspace. Right, so this is basically my whole proof. This is everything I need to show. So let's start by proving one. So one is I want to show that the zero vector belongs to W1 plus W2. Okay, so first part of my proof. My goal here, is show that the zero vector belongs to W1 plus W2. So that's my goal. Now, what I can say is I can say since W1 is a subspace of V, because this is given, right? This is given in the question over here. It says, given that W1 and W2 are subspaces. So we're assuming that's true. It's given to us in the question. Now, since W1 is a subspace of V, then by definition of the subspace, right, so the definition of the subspace is one of the three conditions for a subspace to actually be a subspace is for the zero vector to belong to that set. So by definition of a subspace, the zero vector will belong to W1. So this is just by definition. I'm just stating this because I'm given something in my assumption, in my question, and I'm given that W1 is a subspace. So because W1 is a subspace, I can automatically conclude that the zero vector belongs to W1. Okay, so I know this, right? I know that the zero vector belongs to W1, but similarly for W2, right? That makes sense, no? Because W2 is also a subspace of V. So it's the same reasoning here. By definition, the zero vector also belongs to W2. Now, you're probably thinking, okay, where is he getting out with 0 belongs to W1, 0 belongs to W2? Well, there's nothing wrong in saying that the zero vector, right, is equal to the zero vector plus another zero vector. There's nothing wrong with this statement, okay? But the only thing is that I can say that this zero vector belongs to W1 and that this zero vector belongs to W2 because I've just shown that. I've just shown that here and here. So now I know that my zero vector can be expressed as the zero vector in W1 plus the zero vector in W2. Okay, well, if I go back to my definition of the sum of sets, I said if A belongs to W1 plus W2, then A can be expressed as B plus C, where B is in W1 and C is in W2. Okay, so it's kind of the same thing here. This is like, this is like my A, this is like my B, and this is like my C. So my B belongs to W1, my C belongs to W2, so my A is equal to B plus C, so A, so then A, or in other words, my zero vector, belongs to W1 plus W2. So now I've shown that the zero vector belongs to W1 plus W2. So this concludes this first part of my proof, because there's three parts of my proof. There's three conditions. The first one that I just showed is that the zero vector belongs to W1 plus W2. Now let's go to the second condition. So the second part of this proof is, so let's write, given x and y, two elements x and y, belonging to W1 plus W2. Okay, my goal here is to show that x plus y, so the addition of the element x plus y, where x and y are distinct, so they're not the same vector, because if they're the same vector, that doesn't make any sense. So we want to show that the addition of x plus y belongs to W1 plus W2. So we're going to do this the same way we proved the zero vector. So if x belongs to W1 plus W2, then that means that I can write x as V1, where V1 belongs to W1. So I'm just naming arbitrary elements. I'm not doing anything special. I'm just creating arbitrary elements of W1 and of W2. So x can be written as V1 belongs to W1 plus V2 belongs to W2, because that's the definition of what it means for an element to belong to the sum of two sets. It means it can be represented by the sum of an element in the first set plus the element in the plus an element in the second set. Okay, so I have my x is equal to V1 plus V2. Similarly, if y belongs to W1 plus W2, then y can be written as U1 belongs to W1 plus U2 belongs to W2. So I'm just writing the y element like I did for the x element. So it's just a way of expressing, it's just a way of saying what it means for y to belong to this set. Now let's see what happens if I add x and y together. So if I write x plus y, then I'll get, now let me do this in color. I'll get V1 plus V2 plus U1 plus U2. Okay, well, what I can do now is I'm going to group the green elements, in other words, the elements that belong to W1 together, and the red elements, or in other words, the elements that belong to W2 together. So what I'm going to get is going to get V1 plus U1 plus V2 plus U2. And now here comes the important part. Since W1 is a subspace, it is closed under addition. It's closed under addition. So that means if I write if I create an element W1 that's equal to V1 plus U1, right, where V1 belongs to W1 and U1 belongs to W1, then because W1 is a subspace, it's closed under addition, so this sum, or in other words, I'm just representing this sum by a vector or an element W1, then this thing will also belong to big W1, right? So I'm just saying that since my set W1 is subspace, it's closed under addition. So if I add two elements in that subspace, I'll still get an element that's in that subspace. In other words, an element W1 that belongs to big W1. Similarly, for V2 plus U2, I can write W2 as V2 plus U2, where these two elements added together belong to the subspace W2, because W2 is closed under addition. So what do I get? Starting from x plus y, what I get is I get x plus y, and now I'm just going to substitute W1 as, well, I'm going to substitute V1 plus U1 as W1 and V2 plus U2 as W2. So I'll get x plus y is equal to W1 plus W2, where W1 belongs to big W1 and W2 belongs to big W2. Okay, and so by definition of the addition of two sets, this means that x plus y can be represented by the sum of an element in W1 and the sum of an element in W2. In other words, W1 plus W2. So if you want to go back to the definition I gave over here, right, where I had A is equal to B plus C, where B belongs to W1 and C belongs to W2, then it's pretty much the same thing. It's just that, whoops, sorry about that. It's just that x plus y is A, then W1 is B, and W2 is C. Okay, so I get A is equal to B plus C, where B belongs to W1 and C belongs to W2. So as a result, I'll get that. So x plus y belongs to the set W1 plus W2. So now I've just shown the second part of my proof, right? The second condition of my proof has been shown. And finally, the last part of my proof is given that x belongs to W1 plus W2 and C is a scalar, i.e. C belongs to the real numbers, then my goal is to show that Cx, so rescaling x by C, also belongs to W1 plus W2. Okay, so the same thing that we did in 1 and 2 applies to here. So if x belongs to W1 plus W2, then x can be written as, and here I'll just write it with lowercase. So this is uppercase, W1, W2. So x can be written as W1, where W1 belongs to big W1, plus W2, where W2 belongs to big W2. So x can be written as the sum of two elements, the first one being in the first set, the second one being in the second set, right? Now, what I do next is I rescale the left-hand side by C, meaning that that's just a fancy way of saying I multiply X by C. I do C times X, which is equal to C times W1 plus W2. Okay, and if I just distribute my C here, I'll get C times W1 plus C times W2. But the important thing to notice here, sorry about that. The important thing to notice here is that CW1 also belongs to W1 because W1 is closed under scalar multiplication because it's a subspace, right? Because W1 is a subspace of V, then the third condition, which is W1 is closed under scalar multiplication, holds. So for any W1 in big W1, C times W1, where C is a scalar, will also belong to W1. So again, this is just citing, this is by definition of subspaces. So that's all I'm saying. This is just by definition of a subspace. The same thing for C rescaling W2. This also belongs to W2 because I'm just applying a constant. Well, I'm just rescaling an element in W2 by C, and I know that W2 is closed under scalar multiplication. So this whole thing here will also belong to W2. Okay, and so that means that Cx can be written as, and now I'm just going to write, I'll just write A1 plus A2, where A1 is equal to CW1 and A2 is equal to CW2. But we've just said that A1 belongs to W1 and A2 belongs to W2, right? So that means that Cx can be represented as the sum of two elements, the first one in the first set, in other words, W1, and the second one in the second set, in other words, W2. So that means that Cx actually belongs to W1 plus W2. Well, that's the third part of my proof. I've shown the third condition. So, by 1, 2, and 3, I can say that W1 plus W2 is a subspace of V.